aviso. Muito bem, então, boa tarde, pessoal. Bem-vindos ao nosso colóquio extraordinário. Esse colóquio vai ser gravado, então, se vocês fizerem perguntas, vocês já estão consentindo ao uso da sua imagem e da sua voz. Hoje a gente recebe o professor Hans-Peter Steinrück e quem vai apresentá-lo é o professor Abner, que o convidou. Então, por favor, Abner.
Okay, boa tarde a todos. I switch to English. It's my great pleasure to have here Hans-Peter Steinrück from Erlangen University in Germany. We have a long collaboration through this DEAD and CAPES program of bilateral collaboration, and Hans-Peter was South America and could pass through to give a seminar to us. I would like to give a short introduction from him. He did his studies in physics in the Technical University of Graz in Austria, and then he did also the diploma as equivalent to master, and then the PhD also in the University of Graz in Austria. He moves to Stanford University for a postdoc fellow. And then he becomes assistant at the Technical University of Munich in Germany, did his habilitation there, and then moved to Rutgers University, also kind of a visiting scientist. Afterwards, he becomes associate professor at the University of Würzburg, and from 1998, he is a full professor and chair of the physical chemistry of the Department of Chemistry at the University of Erlangen-Nürnberg in the Bavaria, in the south of Germany. His interest is in surface and interface science. He's covered, I think, a really broad spectrum of the topics, from new materials and novel electronics, geometric and chemical properties at surface, and elementary steps of surface reaction. He can follow reactions at the surface using typical surface science techniques, construction of new equipments also in the apparatus. He has an amazing CV with almost 400 papers in reviewed journals and more than 250 invited talks for international conference and so on. He's also a member of many institutions, also has a long list of awards. He's also did service for many institutions. For instance, also was senator of the University of Erlangen, also was the vice president, I think it's vice rector of the University of Erlangen, also was a member of many advisory board for the scientific conference, journals, was, I don't know if Finnish, was editor-in-chief of Surface Science. Yeah, and thank you very much for coming, and I think everybody will happy to listen to you.
Yes, thank you very much, Abner, for the kind words. And I'm really glad that I finally make it to Campinas, because I have been in Brazil several times, and my co-workers have been in Campinas since 5 years or so, and also some people from Campinas, from Abner's group, were in Erlangen, and but everyone but me made it to come here. This time it fitted really well. And I have chosen a topic that is interesting for Abner and me, and some of the work that I'm presenting, you might have seen some aspect of it with Abner, when Abner was reporting. So what we are investigating here is porphyrins on metal surfaces. I will explain why we do that and how we do that in a little while. So here we have the molecules on this, and that is very characteristic of our studies, namely that we want to follow processes in situ. We want to follow the molecules while they move, while they adsorb, while they react. And I'm an educated physicist, but we moved into physical chemistry. And in physical chemistry, typically, you want to obtain information on kinetics. So we want information on energies and prefactors. And in this case, it's diffusion and reaction. And we do that in UHV, but we also try to prepare our layers in the liquid phase, and I'll also come back to that in a minute. And what we are particularly interested in, if you see here this mobility, can we modify this mobility? Or if you have a surface reaction of the porphyrins, can we modify the reactivity by changing the ligands that we have here at the porphyrin outer sphere? What I'm talking about today is lab Bayes experiments with a monochromated X-ray source, a variable temperature STM work, and temperature programmed desorption. I have to say that we do since nearly 30 years a lot of work at synchrotron facilities worldwide, but I'm not talking about this topic today, but I was extremely interested to see Sirius this morning. It is very impressive, and we discussed maybe to apply for beam time here in the near future, because the possibilities are just fantastic. Where's Erlangen? Maybe not all of you know where Erlangen is. So of course in Germany, I guess that is clear. But if you don't know where it's exactly, then here's Frankfurt and here's Munich. These are the typical two airports where you fly in to Germany, and just in the middle, half distance, 2.5 hours to Frankfurt, 2 hours to Munich, there's Nürnberg and Erlangen. And Nürnberg is a city with 500,000 people, Erlangen with 100,000 people. They grew together, so it appears as one city, and the university is the University of Erlangen-Nürnberg, so a university of two cities. The major focus on natural sciences is in Erlangen. This is the name of our university. Our former president was proud of having the university in Germany with the longest name. That is not always an advantage, because if you always say Friedrich-Alexander-Universität Erlangen-Nürnberg, you spend so much time. So we call it FAU now, in order to abbreviate that. And it's from the size, it's I think pretty similar to your university. So we have roughly 38,000 students. It's relatively old, 275 years. The funny thing is, it was originally in Bayreuth. But the problem in Bayreuth was that the soldiers were also in Bayreuth. And so the young soldiers and the young students were having a lot of fights and shootings and killings among each other. And the solution to that was to bring the students to another city. And the other city was then Erlangen, and therefore the University of Erlangen was founded. We have 5 schools, or faculties as we call that. Faculties are similar to what you call institute here, because the faculty is the highest unit, and departments are below the faculty. So we are in the faculty of the sciences with mathematics, physics, chemistry, biology, and geosciences. And then we have engineers, we have medical doctors, we have business and law school and humanities. And what my group particular does in Erlangen is surface and interface science, so very similar to the work that Abner is doing here. We do fundamental research. We try to research on new materials. So we prepare, 2D materials on the surface and characterize them. Then we want to follow the elementary steps of surface reactions on the surfaces. So here you have a single crystal surface. You come in with methane. Methane is a very stable molecule, so if you want to adsorb it, chemically adsorb it, chemisorb it, you have to break one CH bond, which is very hard, and we try to find out what can you do to do that, and then we want to understand the following steps. And then if you do that long enough, you form molecules, decompose molecules, you end up with carbon, and if you do that long enough, you get graphene, if you do it right, at the right temperature, right conditions. And often we are not happy with the experimental equipment that is available. Then we build very specific equipment, typically from commercially available components ourselves. So this here is an XPS machine, for instance, and our idea was we want to do angle resolved XPS on liquids, special liquids that don't have a vapor pressure, like liquid gallium, for instance, or ionic liquids don't have a vapor pressure, so you can go into vacuum. But a liquid is a liquid, and if you want to do an angle resolved measurement and you tilt the sample, the liquid is gone. So the question is, what can you do? You can rotate the analyzer or use two analyzers. That's the cheapest solution. This is only 100,000 euro, but all other solutions are close to 200,000. If you have a rotable analyzer, that is pretty difficult. Okay, so this is also what we do. The topics that we're interested are in situ studies of surface reactions. So we want to follow, I said that already, while processes occur. And now comes a class of materials that we're interested in studying. One of it is liquid organic hydrogen carriers. The big topic here is hydrogen storage. We all know why that is important. I think in this audience I don't have to explain. The problem is that the conditions you store hydrogen are either high pressure, 800 bar, or low temperature liquid helium, which is both not really convenient. But the very simple way, and this was initiated by BMW in our labs with the engineers, and we collaborate with the engineers here, would be liquid organic hydrogen carriers. These are molecules that can store hydrogen. As an example, which doesn't work because of the energetics, is not really favorable, but for the understanding. Imagine you have benzene, C6H6, and you fully hydrogenate benzene. You have C6H12, 6 hydrogen atoms or 3 hydrogen molecules stored. And for materials of that class, if you have 100 kilogram of substance, the hydrogen that is stored in there is enough to run a BMW 500 kilometers. Similar to a full gas tank of a car. And the advantage is, these are liquids, you could use the gasoline distribution system that we have, which is based on liquids, just as it is, without, the only thing would be that you go to the gas station, you have one pump getting the liquid that is used, the benzene, out of your tank, and another pump that refills the other liquid, which is technically not so much more difficult. Benzene there are too high activation energies, benzene cyclohexane, so you have molecules where you have nitrogen in, and so that lower these activation energies, and there's a lot of research going on this type of molecules, and in Bavaria we have a project where we, together with the engineers, have the goal, 25 million euro is the sum that we have available, to replace a diesel engine driven train by a LOHC driven train. And of course, at the end of the day, you have a fuel cell. The fuel cell then converts the hydrogen to electrical power. And our understanding is what we contribute is doing model studies where we try to get the individual steps that you have here in this type of reactions, also for these more complicated molecules. Then we modify graphene. So we somehow try to link molecules to graphene. We work with liquid metal alloy catalysts. These are very specific systems like platinum in gallium, where then individual platinum atoms swim at the gallium surface for short periods of time. And then there are so-called single atom catalysts. And these catalysts don't coke. Because for coking, you need to break a carbon-carbon bond, and you need 2 adsorption sites for the product. If there's only one platinum atom, you don't break the bond. Then we work with ionic liquids. Ionic liquids are liquid salts made of molecules that are liquid at room temperature and have no vapor pressure. There's no system with no vapor pressure, but a very, very low vapor pressure. And finally, we work with porphyrins, and I'm interested in the surface chemistry of porphyrins. And this is the topic of today's talk. Okay, So what is a porphyrin? I guess many of you know, but as I'm in the physics department, I repeat it. Being a physicist myself, when I started in physical chemistry or with this project, I didn't know what a porphyrin was. No idea. I couldn't even pronounce the names of the more complicated ones. I'd still have a hard time there. So the porphyrin is a macrocycle. The macrocycle is composed of 4 5-membered rings with a heteroatom, a nitrogen atom here. 1, 2, 3, 4. And that are connected by methane bridge, so 1 carbon bridges. It's fully aromatic. And if you look at the nitrogens, you have 2 types of nitrogens, one without a hydrogen and one with a hydrogen. And I will come back to that a little later. If you do XPS, these 2 are chemically equivalent, and each of them gives a peak in XPS. So you see 2 peaks in XPS if you have this type of system. And this will be very important for the talk. And these molecules are really, really important in nature. They make up all the colors, or many of the colors, together with phthalocyanines in nature. And if you have here this porphyrin, and the porphyrin, you can put a metal atom in the center. If this metal atom is magnesium, you have chlorophyll. If the metal atom is iron, you have heme, responsible for the blood transport in your, the oxygen transport in your blood. If you have cobalt, it's vitamin B12. So this is nature, but all these examples also are used in technical applications. So here you build applications for light harvesting. So you convert solar energy into electrons and at the end of the day, electricity. The second example is colorimetric sensors. So color metric sensors. So you have this arrays of porphyrins on surfaces, and then you have different metals in these arrays, not the same but different. And if a molecule absorbs, the color response to a particular molecule is different for the different metals, and from the color pattern you get, you can identify molecules. And the last example is using these as molecular catalysts, so metal complexes, where you do homogeneous catalysis and then you can have certain reactions. Or if you anchor them on surfaces, you also can do heterogeneous catalysis. So in our job or our game or the fun that we have now is that we put them down on metal surfaces, because in all these applications you see the porphyrins are put down on the substrate. Here typically it's titanium dioxide, here you see it's a sandwich substrate, and here this is in the homogeneous phase. So often you put it on a substrate, and our goal was now put them down on solid surfaces, because the surface plays a role in them. We can try to see which properties can we vary. We can vary the side groups. So down here, an example, here's a surface, single crystal surface. We always use single crystal surfaces to have very well-defined systems. And then you have a porphyrin, there's a tetraphenylporphyrin, so phenyl groups here, and the molecule has a certain distance to the surface. And you can measure that, for instance, with standing wave techniques. And then the metal atom has this distance. If you have more bulky groups, then this distance is increased. And of course, the electronic interaction between this here and this here is modified. The next thing you can do is you can change the metal atom in here. You can do 3D metals, you can do 4D metals, you can do no metal, this would be the free base porphyrin. And all that results in different properties. You can, of course, change the substrate. These are the substrates that we investigated, so metal, relatively inert metal surfaces and oxide surfaces. You can even absorb, so mimic the effect of oxygen transport in blood. In a way, you absorb NO or NH3 on the surface, and then you get something which I don't address today, is the surface trans effect. And that is our playground. And I start out with modifying the surface and see what happens if you modify the surface and what different phenomena you can see. So we vary the substrate. It's a free base porphyrin here, so no metal atom in yet, on silver and on gold, and on copper. Okay, on silver, the system is very simple, nice. What you do is you have a surface, you deposit the porphyrins, you just evaporate them onto the surface in vacuum, and then you get the perfect two-dimensional structure. Hexagonal surface, quadratic lattice. This is an indication that the order on the surface is dominated by lateral interactions. So the molecule-molecule interactions are the origin of this order of this quadratic lattice, and you find islands starting at low coverage because the molecules want to agglomerate. Also indicative of lateral interactions is the fact that if you exchange the metal if you put in a metal atom or exchange this metal atom, you always get the same appearance, the same quadratic lattice. Of course, you can look a little more detail to these molecules, and then you look here with better resolution, and then with this better resolution you see that you see this molecule here. This is the molecule. Here you have 4 side groups. These are the 1, 2, 3, 4 side groups. And what you also see, the molecule doesn't have a 4-fold symmetry, but a 2-fold symmetry, and this comes about because the molecule wants to get as close as possible to the surface. The phenol groups could stand upwards, then you have a large distance, but if they tilt down as much as possible, until the hydrogens here have steric repulsion, you get it closer to the surface. This leads to this saddle-shaped type deformation, 2 pyrrole groups looking towards us and 2 looking towards the board, and then this appearance, saddle-shaped deformation. So that is a relatively simple system, and it took us a while to get used to that, but then it is pretty easy. Then we move on to copper. And with copper, the story is completely different. If we go to the copper source, we don't have ordered layers. We have disordered adsorption, seemingly disordered adsorption, because we see individual molecules, they look a little like butterflies. There are 2 bright longish protrusions and a dark line in between. And if you look in a little more detail, they are not really randomly oriented. There are only 3 types of orientation. This is going up in this direction. This is the same, this, many of them. And then there are some that are rotated such that they point in this direction, like this one, or this one, or this one, and then there are some that are rotated in the other direction. So rotated by 60 degrees, so that's the symmetry of the substrate. So obviously what happens here, these molecules want to bind in a very specific site to the substrate. There is obviously a covalent bond of these molecules to the substrate, and therefore they are so highly oriented. This is now the high resolution image. It looks a little different than the saddle-shaped deformation. And then, what is the reason for this orientation? The chemists immediately would say, oh, that's not so surprising, because nitrogen wants to interact or does interact strongly with copper. So we form strong copper-nitrogen bonds, and there we bind covalently to the substrate, and that gives you then a very well-defined orientation. This well-defined orientation, or this specific adsorption site, is also reflected in XPS. Let's start with a system that is very easy, namely this is multi-layers of porphyrins. So you only have porphyrins, no substrate, no nothing, and it's a free-base porphyrin. There's no hydrogen, there's no metal atom in, and so you see you have these nitrogens without hydrogen, and this with hydrogen. I told you that before. 2 peaks. This is the chemical shift because they're bonded differently. The intensity is 1:1 because this is 2 and this. And if you now adsorb this molecule on an inert gold or silver surface, where there is no specific interaction with the substrate, we saw this on the slide before, then the difference in binding energy of these 2 is maintained. They shift a little. That has to do with the relaxation effects in photoelectron spectroscopy. You believe me that this is not really affecting the molecule. But if you go to copper, the distance 2 electron volt shrinks to 1.5 electron volt, and this reflects the interaction of these copper ions with the substrate. It's called a chemical shift because of a chemical interaction. Okay, now we come to a little difficult point for all people working with STM, because you don't always have what you believe to have. And here we have a very classic example. If you do STM, and the interesting thing is, after observing it ourselves, we went into literature and we also found it in other papers, that the same molecule, one sometimes looks like that, and sometimes looks like that. So here you have this longish protrusion here, and here you have 2 bright protrusions in here. It's the same molecule, nothing happens. It's only a different tip. And now the question is, what can we learn then from the absorption geometry if we have these different appearances? So theory is typically of help there. You ask the theoreticians, friends that we have in Erlangen, to do a calculation on the energetic stability of the molecules on the surface. And the colleagues did that. They calculated this saddle-shaped type deformation, and the molecule looks like that. And then they calculated what is called an inverted structure. There you flip one of the pyro groups completely 90 degrees out of the molecular plane. And if you do the calculation, you find this is much, much more stable than this one. The appearance is the same. It's always this molecule, but we are fooled by the nature of the dip. So the stories on what I told you before are unchanged, but the appearance of the molecule could be like this or like this, and then the rest is the same. Okay, we rule out this one. Okay. Then you saw that beforehand, this was my introductory slide, that the molecules move on the surface. These are the molecules. How do we do that? So we take a movie. That means we measure STM image after STM image after STM image of the same area on the surface, and then we add these images one after the other, like in a frame of a movie, and then we have an endless loop, and these are, I think, 25 images, and then we show it like that. So it's a really super slow motion of the actual motion. And what you see is they move, but they don't move randomly. They move here up and down. This one here. And these move, the ones that are oriented like that, only in this direction. So the molecules, they behave like a train on rails. If you are in the rails, you just can move in the direction of the rails. And this is what is happening here. We have unidirectional motion along the densely packed rows, and it has to do with the fact you have a covalent bond, and the molecule can hop to a neighboring site with the same covalent type of bond. So this is schematically shown here. They move along the densely packed rows of the substrate, and a 60-degree rotated would be this direction, and minus 60 degree would be movement in this direction. So as I said in my introduction, we are physical chemists. We want to get numbers on the kinetics. So you need brave students, and you need modified experiment. Here the coverage is high, and you could say anything you measure could be influenced because of the molecules collide with each other. So what we did is the following. We went to a very low coverage. And then we said, okay, we don't want the molecules not to move. And if you want them not to move, then you go to low temperature. So if you go to low temperature, and this is the molecule, you see it isolated, and then you measure, let's say, I don't know, 20 STM images, photographs one after the other, and if the people don't move in your object, you get sharp picture. And this is what we have. The people, the molecule didn't move. Next step was we increased the temperature, then the molecule started to move. So you see here this superimposed 25 images, and you see the molecule move. And the molecule moves in one direction, like a train on rails. So we have an unidirectional motion. And then the students had to count. So we did images at different temperatures. Here you see low temperature. We color-coded individual molecules, and then we looked, superimposed again these 20 images, and then here you see nothing happens. So all people on the photograph stayed at the same spot, all are sharp. And then you increase the temperature, and you see they move in one certain direction or in this direction. And you increase the temperature further, then you see this direction, vertical, and this direction. And then if you go too high, it's getting a little chaotic, although the same behavior is still there. And what you see here and here, sometimes they change their direction. Sometimes, obviously, the energy is high enough to rotate by 60 degrees, there's an equivalent direction, and then they move in the other direction. So what you now have to do is you have to count the hopping rate, the hops at these individual temperatures. And that's what the student did. They counted the hops, and we plot here the logarithm of the hops, the number of hops, and plot it versus 1 over temperature. So this is the typical representation of an Arrhenius law. And what we see is a straight line. And if you have a straight line, the immediately can get the activation energy for this process, and this is 0.71 electron volt, and the prefactor is 10 to the 10. And then we can do the same analysis for the number of changes of the movement. So we call that rotation because the direction is rotated by 60 degrees. And again, we get a straight line, and we get a higher activation energy because in a very simple picture, this occurs more rarely, but on the other hand, it also the prefactor changes. So that's a little more complicated, but I don't go into the details here. Okay, so this is a work that is relatively old. This is 10 years old or so. And so we could quantify that, and that was really nice. But in the last years, we asked ourselves, is there a chance to change this property mobility, to change the activation energy by modifying the molecule? And so what we did is we changed the periphery here. So we went to this molecule from here having phenyl groups to having naphthyl groups at the periphery. And then we image individual molecules. So this is the one shown here. And this is the one with the naphthyl groups. You see, it's more extended here because these groups are even more extended. Or down here is an image superimposed. But now there's a new complication. The new complication is the following. The first complication, it's too warm for me. If you don't mind. There's a new complication here, and I also can do better without my jacket for this new complication. You will see in a minute. Namely, you have this naphthyl group, and you can imagine that this naphthyl group can be arranged in a way that it points outwards, but this is a single bond, so the whole group can rotate by 180 degrees, and then you get the species where the second ring is mounted here. So in a way, the molecule looks either like that or like that. And then you can do this for each of these groups. So you can have a molecule that looks like that, like that, whatever. And you have two species. Each you can rotate, so you have 16 different conformations that are possible. And then we measured on the surface, and indeed we found, so if you look at this one, this looks pretty large, and this one looks pretty slim. And then we looked much more careful, and then here I added 3 images and color-coded different shapes. So if you look at this shape, this is this guy. And if you look, for instance, at this one that looks like a K, this is this guy. And out of the 16 possible conformations, you will only observe 10, because for 6 you have a rotamer. That means if you rotate by 180 degrees, it looks alike. And that's, of course, you cannot differentiate. And that's what we did then. So we identified all of them. And if the guys are looking outwards, we call it alpha. And if it's inward, we call it tau. And so this is our alpha friend. Like here, then we go to the tau friend, tau, all are close, and then you can go through, we have a K, here we have the rotamer, because if you rate by 180 degrees, it's a different appearance. This would be tau, alpha, tau, and this is alpha, tau, alpha. And then you have a tau type, and then Y, I don't go through all the details. Interestingly, some of them are chiral, and some are achiral, and then we here, for instance, we have a windmill type, and so on and so on. And we found all of them on the surface, and don't forget, we are always working at room temperature. This is not helium temperature STM, this is really at room temperature. And then our basic idea was what happens to mobility. And if you look now at the molecules on the surface and superimpose again 10 images, you see you have some of them moving, and some of them not moving at all, and some of them somewhere in between. So if you follow the tracks, you see that immediately, so these are moving, the red ones are not moving, and these yellow ones are in between. So we define 3 categories: slow, medium, and fast. Slow is red, medium is yellow, and fast is green. And how fast they are, or how slow they are, that depends on the orientation of the naphthyl groups. This is again our table, and then I indicated the mobility with green, yellow, and red. And if you look to the green ones, you have 4 or 3 taus. So the straight ones, the slim ones, and the red ones, you have 3 or 4 alphas outwards, and the yellow ones have 2 of each. And so obviously the footprint of the molecule is responsible for the mobility on the surface. And if you now heat your layer that I showed you to 400 Kelvin, you observe that they all look alike, and they all look like the alpha, alpha, alpha. So that is obviously the most stable, and the most stable one was the one that was not moving, likely because it had the deepest adsorption well, and therefore it didn't move. Okay, this was the first thing, this was the mobility discussion. The second thing is a reaction of the molecules on the surface. The reaction is the following: if you deposit this molecule on the surface, and you might know from Abner's work also that you can coordinate molecules, atoms within the molecule. So we have a reaction, the molecule is adsorbed on the surface, a metal atom comes from the gas phase, and we form a metalloporphyrin, like the magnesium or the iron or the cobalt porphyrin, and the hydrogen is released to the gas phase. Very simple. So there's no molecule in the pocket, you add a metal atom, then you get the metalloporphyrin. Very importantly, if you look now at our nitrogen atoms, these are inequivalent, and these are equivalent now. So here we should have 2 peaks, here we should have only 1 peak. And this is exact, and you can do that with many, many different metal atoms. And the signature of the nitrogen atoms is typically what we do to identify. The process is very simple. You deposit the porphyrin, you deposit the metal, and it turns out that for most systems, and particularly if you use some additional heating, you get the same result. So it doesn't matter what you put down first. And XPS is a very nice means of following it, because here I show the XPS spectra of this one you have already seen. This was the monolayer on silver, 2 EV separation here. The molecule doesn't interact with the substrate. Then here, down here, we add the metal atom in the center and deposit this to the surface, the intact metallated one, and see you only 1 peak. And the intensity here is 1 to 1. And if you add these 2 peaks in intensity, you get the peak of this height, but at a different binding energy. So this is our signature of the metallation. And then we take the molecule and then deposit the cobalt. And if you deposit the right amount of cobalt, so that you have exactly 1 cobalt per porphyrin, then you get exactly what you expect for the metalloporphyrin. So we can metallate on the surface. Some people don't believe in XPS. You would not imagine, but this is the case. So we also did STM, and you will see then I also showed you some STM images here. So here you see you increase the amount of cobalt, and you have a chemical contrast between the species. The free base is dark, and the cobalt is light, bright. Okay, but then we thought, okay, if you deposit the metal on a metal surface and you get the reaction, actually on a metal surface there are a lot of metal atoms to begin with, because it's a metal surface. Would it be possible maybe to react with the atoms of the substrate? It does not occur in silver. We never saw that. But then with copper, we had this strong interaction of the nitrogens with the substrate that you thought, okay, that could be possible. And indeed it is. So if we deposit at the room temperature where we did our diffusion experiments, we saw no reaction. And in the XPS, we see the 2 peaks. But as we heat then to 450 Kelvin, we see only 1 peak. So obviously, it picks out the copper atoms from the substrates, or takes atom from a 2D gas of copper atoms on the surface and inserts them in the species. And STM, you remember, this is the 300 Kelvin species, was this species here with this longish dark line in the center. And this species we could image at room temperature. You remember that these were the moving molecules, we could see them. If we have the cobalt porphyrin, the copper porphyrin, sorry, you saw that we had on the surface where it was not interacting, the metalloporphyrin is inserted, and then all the nitrogens bind to this copper, and then the nitrogens don't interact with the substrate. So this molecule is extremely mobile and forms islands on the surface, so you cannot even image it at room temperature at low coverages. So you have to cool, and then you can see it. But room temperature, you don't see it. If it's cool, you see it, it looks like that, completely different like that. Okay, this is really nice, because what you can do now, if you are at room temperature, and follow, and shortly heat to 400 Kelvin, some molecules react, you cool down, then you should have a decrease of the number of these species, and the others you don't see. And this is exactly what's shown here. So we put the molecules on the surface, we have less resolution in the larger surface area, and then we heat, and look how many of these protrusions, which are the free-base porphyrins, do we have. So here we have all of them, because we did not heat, and then we heat it for 40 minutes, and then for 160 minutes, and you see the number of bright protrusion gets less and less, and in between you see this greasy stuff. And this greasy stuff are the molecules that you cannot image. And now you do a very simple chemical reaction analysis. You count, like in radioactive decay, the number of atoms that are not decayed yet, you give, so to say, have a starting signal, and then they decay, and then you have less and less. And this is the same here. You just count the number of bright protrusions. And then you plot the number of molecules, and if you're clever, you plot the logarithm of them as a function of time. If you plot the logarithm of a concentration as a function of time, and you get a straight line, you have a first order reaction. Like radioactive decay, you have an exponential plot decay, and if you plot the logarithm of an exponential, you get the linear behavior. And the slope gives us the and then we do an Arrhenius analysis of these slopes. And this is shown here, the Arrhenius analysis of the slope, so ln K versus 1 over T, and we get the activation energy for this reaction. 1.48 electron volt. Yeah, this is the Arrhenius equation for those who have forgotten it. And we can even with SDN follow this reaction a little more detail. What we have seen in the last image was the following. We have started out with the free-base porphyrin, and then we inserted the metal atom, and then we released these two hydrogens. And then we have the metalloporphyrin. But if we heat further, we observe a very strange behavior in STM, namely that the molecules start to look like that, and then like that. And what is the explanation? The explanation is a chemical reaction. What happens is the following. You have here this hydrogen and this hydrogen. And if you heat high enough, the same here or here, you abstract these hydrogens. And, you abstract these hydrogens and you form a CC bond. So you form a CC bond here and a CC bond here. These are single bonds, so that these groups are rotated. This is now double bonds, and this whole thing is completely flat and aromatic. So this appears lower in SDM than the non-reacted part, which you then can open, and then you get to a molecule that's completely flat. So we dehydrogenate, and we have used two hydrogens here, two here, and these together are four hydrogens, making this molecule from here to flat. So I talked about what's going on the surface, but we can also watch these hydrogen atoms, actually molecules, released to the gas phase, and there's a technique that allows you to study that, and this technique is temperature programmed desorption. So what you do is you just have, it's not really that simple, what you have is a mass spectrometer, and you sample, and then you put the mass spectrometer in front of your sample, and then you have a glass tube that gets with a narrow hole in front, and you bring this hole very close to your surface, that you only see desorption from your sample, but not from your sample holder. Sample holder desorption is typically coming everywhere. And that's what we did. And I only want to make a long story short to discuss this picture here, which we have up from a certain coverage on. What do we see? Remember, first step, we lose one hydrogen molecule. Second step, we lose 4 hydrogen molecules. And then there are 10 left, and we lose them at high temperature. And we observe in TPD one small peak, one larger peak that is 4 times this small peak, and then a very large peak that is 10 times this small peak. And how do we find out? It's very simple. You just integrate the spectrum, and this is shown here. You integrate the spectrum, the first signal increase, then you integrate, you have another increase, and then you have another increase, and then you say at the end of the day, I have 16 hydrogen molecules in my molecule, and 15, sorry. And this is gives me the scale up here, and then I get the scale, and then if I look at the scale, I just add, see that this is 1 and this is 4. So exactly what, in line with what we proposed from STM. Okay. So this is also a while ago since we did that. Not this one, but the first metalation studies were a while ago, and then we did the temperature program. Study, and then we said, okay, same question, can we modify that? Can we modify our molecule and thereby change this reactivity? And we did that by introducing cyanogroups. So we have this tetraphenylporphyrin, and then we introduced 1 cyanogroup, we introduced 2 cyanogroups, we introduced 4 cyanogroups. And then we studied the decay of the density on the surface. This blue curve is what we have seen already with the activation energy of 149. And you see, as we add a number of 1, 2, and 4 cyanogroups, the reaction gets much slower. Factor of 20 slower. And we can also plot these curves again on the logarithm scale, as we have seen it before. The slope here is steep, the slope here is flat, and if we is that the Arrhenius equation, and we assume that the prefactor is the same, and then we know that here is the activation energy 1.48 eV, and then we can calculate the activation energy that is necessary to get the reduction of the slope of the reaction rate by a factor of 20. This is 159 electron volt. So by introducing these groups here, we can modify the reaction rate as we want. This is nearly this part concerning metallation. But, I want to show you some side effect which is pretty nice if you work with these molecules. If you absorb them at room temperature, you also find a very nice ordered structure on surface, long-range order structure, and the structures get even nicer if you heat to higher temperatures. You get structures that look like snowflakes, and you can go even further if really you heat higher coverages, and you really get well-ordered networks on the surfaces. And the interesting point here is that this reason for forming these networks is that you not only can insert the metal atom in the center of the molecule, but you also can coordinate the cyanogroups of this molecule on the surface with copper addatoms. And these copper addatoms, this is the driving force for the formation of all these ordered structures. And I don't want to go into the detail here because I have a short last chapter. You also find it on other surfaces and with other always on, not other surfaces, other porphyrins, here with benzo groups. On copper, you find here really beautiful Kagome lattices or quadratic lattices. This is the same. These are coexisting structures on the surface, and it's always the cyanogroups connected via copper atoms. The last short topic I'd like to address is what happens if one goes to the liquid phase. And why is this important? First, this is important because if you think of any technical application, preparing such layers on surfaces by evaporation is not really a realistic way of preparing hundreds of square meters. So here you have to go to liquid phase preparation, but if you have work with liquid phase preparation, you typically have some challenges. So what we talked about is metal vacuum, and we also studied oxides. I'd skip that today, and now we go to the liquid phase. And Federico Williams, that some of you know, he's from the university in Buenos Aires, and he measures every once in a while here at the synchrotron. He developed a setup where you first prepare your sample in UHV, using the standard methods with well-defined ordered layers, and then he transfers the sample in the so-called liquid cell, rotates it by 180 degrees, so it's upside down, lowers the sample into an electrolyte here containing, for instance, metal ions, then pulls it out, rinses it with hydrogen, blows it dry with argon, moves it back to the UHV system and analyzes. And we started 3 reactions. The first one, metallating a free-base porphyrin with zinc. The next one, removing the zinc and replacing it by copper, so exchange. And the last one is getting out the zinc and getting back to the first one. That's demetallation. Concerning metallation, this is the experiment, or the result of the experiment. We start out with the clean surface, so there's nothing on the surface, flat background. Then we adsorb in vacuum the free-base porphyrin. We have the well-known 2 peaks, so we have our porphyrin on the surface. Then we expose the surface to the zinc acetate in the liquid cell. We get these new and taller peaks, so this is the sum of the 2. So we have a metalloporphyrin, but we have something else which we don't like. But the nice thing is, if you heat to 250 Kelvin, what we don't like goes away. So the contamination goes away, and we have the clean zinc porphyrin. And if you compare that to a zinc porphyrin prepared in UHV, you see perfect agreement. So that works. Second, can we replace the zinc by copper? Experiment is relatively simple, and the answer is also relatively simple. We start out with the zinc porphyrin to the copper-containing solution. The zinc nearly disappears. We get a new peak here, which is characteristic of copper. And we get also, we keep the metalloporphyrin, though we have some contaminations we couldn't get rid of. If we compare that to the copper porphyrin, it fits again very, very well. So we can also exchange the metal center. And the last step then is the demetallation. And sometimes things just don't work. And that didn't work. So the last one didn't work. And I skipped this interpretation here and come to the summary. So I talked about metallation of porphyrins and metals and oxides, about mobility, adsorption on crystals. I talked about functionalization and how we can modify reactivity, and here we modified mobility, and I talked a little about, very briefly, about networks, and then about liquid phase reactions, metallation, metal exchange. And of course, one should never end without thanking the people who did the work. So it's Hubertus Marbach, he was here, with his students, and Simon Sieckel was here, Michael Lepper was here, and also Jan Kuliger was here in the group of Abner doing experiments together. And the team of Ole Lütken, who does the XPS part, Hubertus does the STM part. And then, of course, I would like to mention the collaboration with Abner, which was on the metallation reaction, on the network formation, and the collaboration with Federico Williams, also from Latin America. With that, I would like to thank you for your attention, and I hope I wasn't too long. Thank you very much.
Wow, thank you for the very nice talk. Very impressive what you can do with porphyrins. Now we go to questions from the audience? Do we have any? Oh, while you think of questions, I have one at least. On your first slide, you show us this beautiful video of the porphyrins moving around. How long is a frame in that video?
So I can give you the rough number. A typical image takes 5 minutes, and then you add the minute like 20, then you have 100 minutes, but you compress it and maybe down to 10 seconds.
Okay, so each frame step is 5 minutes.
Roughly, yeah.
Okay.
Maybe 7, maybe 3, but this is the order. Might also change a little from image to image.
Essentially, they are fast, but not that fast.
You have to think, exactly, they're fast, but not that fast. Because if you think of the prefactor that is relevant, which is typically 10 to the 13th, then it's not too many events. Because otherwise you would. And this happens if you have a metal atom in, then they're so fast that you don't see.
Exactly. The super fast ones you simply cannot image.
Exactly.
Because while you are scanning, they are moving around and...
Yeah, exactly. Then you see fuzzy images. But sometimes you catch one under the tip moving for a slow distance, then it goes away again. You have fuzzy, big images.
Very nice. You have questions? All the way back there. For all the students, the QR code is... no, it's here. So, pass it around.
Thank you for your presentation. I'd like to ask, when you show the two configurations of the porphyrin, the inverted and the several, I didn't understand correctly, but does the porphyrin like move between the configurations due to thermal fluctuations, or they settle in one or the other?
In one image, you see only one configuration. So it either all look in this image like that, like the butterflies, or because it depends on the condition of the tip. And it might happen sometimes that you see, if you scan from top to bottom, that in the upper part of the image, because you go likewise, you have one appearance, and in the lower part of the image you have the other appearance.
Because the tip changed.
Because the tip changes, yeah. What exactly changes is, I guess, that happens often in STM, and you hardly know what it really is. But if you're really good, then you can functionalize the tip with a CO molecule, and then you get these super nice images, but that is then only at 6 Kelvin and not at room temperature.
Thank you.
And more questions? One? Do I have another question? Oh, Abner has a question.
You showed this application of using porphyrins for other molecules to kind of PV, solar cells, or things like that. What would be the more critical thing? You have to have connections between the molecules to separate the charge, or would be the interaction of the molecule with the substrate? What do you think is the most critical part? Because the molecule is an absorber anyway for the light.
Yeah.
It's a good absorber.
Yeah, that's a very good question. Of course it's for Abner. No, the point is that you have to get the charge from the molecule into the typically TiO2 substrate. And then the question is, how do you anchor the molecule? So you have to somehow anchor the molecules covalently, otherwise you don't get the charge across. But then the point we typically do not address here is what is the alignment of the levels of the molecule relative to the levels of the TiO2 for the charge transfer to be possible, but also not to lose too much of the energy, because you can fall down too high, because then this energy is lost. And so the one important point that we also did quite extensively with Federico is, how can we bind the porphyrins to oxide surfaces with functional groups, like carboxylic acid, phosphonic acid, hydroxamic acid, boronic acid, and this is a topic that we follow up. So it's the energy alignment that determines whether something is working. And of course, there are some other steps, but I'm not a technology person, so I would not dare to go deeper here.
Well, one trick is to not have the recombination.
Exactly, that's what you have to avoid. So you have to get the charge away quickly. If the charge stays too long, it will go back. So you need sort of a gradient where the charge has an energy gain if it goes away. And this gradient has to be high enough that it does, and then the electron can go into the oxide surface.
Okay, more questions from the audience? No? I have two questions.
Okay.
So, sorry. First one, going back to that video on the first slide.
Okay.
Because the molecules were moving around nicely, but I noticed that you had something that looked like grain boundaries on your surface.
Steps typically, terraces.
Steps. So they are terraces,
yeah.
Because they were stuck on the terraces.
That's a very typical situation that because you observe this quite often, it's very convenient to link to the wall. You have a higher coordination. And typically the species on surfaces, typically, if they're not charged, because if there's a charge, then it's repelled, then it might be different. But if not charged, they like higher coordination. And if you look at island close typically starts at step edges. Not exclusively, but often typically at step edges because of this higher coordination, which indicates that the bond at the step edge is stronger than on the terrace. And if the bond is stronger, it doesn't move away.
Thanks. And for the nice lattices of porphyrins that you've shown us, first, can these be used as scaffoldings to assemble something on top, like a monolayer of some other material, or?
I have to think a little. The thing is that the free-base porphyrin itself, there is. This is a more complicated answer. So what you need is something to dock on. So where could you dock on? You could imagine you dock on a metal center, because that's what's happening in heme, for instance, when the molecules dock on, and if this bond is strong enough, you can have that as a starting point to go. You want to go in a certain dimension. That is one point. The other points would be that you have the ligands, that, like the CN groups or so, that you try to build ligands that would also allow to dock on from a next layer to this porphyrins. But it's not what a different system that Arne, I guess, also studies would be a graphene moray on the surface, where you have a valley and hill structure or an HBM structure, where you then put something in the pore. And then you get, and then you can maybe put a metal cluster in the pore and then connect something to this metal cluster. So the options are many, but what we did more studies, what we are interested in is also if you have different porphyrins on the surface, are there replacement effects? So I have porphyrin A on the surface, deposit porphyrin B, which porphyrin, if then you heat, provide thermal energy, and then if the stronger bound will go to the surface, the less bound will be above, with some entropic disorder. And these things we studied, but we didn't study using them as a starting point for architectures. That was not our. And the problem with that is that going in the third dimension with STM is very hard. It's much better. You can do that with AFM, and if we now have an UHV AFM, where we have for several studies, we could see order in several layers. But this is not. This was ionic liquids. This was not perfect.
I see. Thanks. And questions from the audience? Okay. Another question from the audience.
With smart, so I have to think about it.
Okay.
I just would like to ask a very question with respect to this test. didn't realize that it had an effect on the shape of the molecule that you were looking at.
Okay, I can go there.
So, what I would like to ask is linked to the any effect of the bias voltage that you also have shape that the molecules get. And yeah.
What was that? So this was it. Disappearance or disappearance coexist. And yeah, tip is very important. So in all effects, particular diffusion, or we also studied switching of porphyrins on surfaces, you have to be very careful with the tip. So what we did is we changed the voltage. We tried to get the current low. We changed the speed of the images just to see where is an influence of the tip and where is not an influence. The modes that we typically use is the topological mode. So that means the appearance is stable over a relative wide voltage range. So it's not that you have, like with the cobalt porphyrins, at 0.6 CV, there is a occupied state due to the interaction with the substrate. And if you go there, they are particularly bright. So we try to avoid that and work in a range where the appearance did not change with voltage. Also check with positive and negative voltages. Typically, you also always get images, and then you take the appearance which looks nicest. But the effect is all what I have shown you is independent of dip effects. But there are dip effects. You can have snowblow-like effects where you really see which direction you have moved. If you go too close and too rough in tunneling conditions, you see it. That is always with SDM you have to be avoided. It's really also this one here is really, this was really scaring a while because then we looked in literature and we found in other papers exactly the same. Some commented and some uncommented, and then we said, okay, that is, and it was always that people said it's not different species, it's a different.
Question. As STM is also very well known for spectroscopy capabilities.
Yeah.
I don't think you mentioned a lot about those. Are there interesting things to study yes, as it's not?
Yeah. The problem is a little that if you work at room temperature, you always find drift. And that is something you can do. Drift compensation, that you always keep the same image in the center of your so that you don't lose the image. But if you want to do spectroscopy, you want to stay in the same spot and not have the sample drift away. Because statistics is not nice to you, so you have to wait for a while in order to get a nice spectrum. And that is difficult at all. We try to do it. For instance, with this cobalt porphyrin in UPS, we see a peak at 0.6. We see the same peak in the tunneling curve. But this is a large peak and it's easy to detect, so this is consistent. But going much further is very hard, and therefore we said, okay, the other people that can, because our microscope doesn't, the lowest temperature is 180, we don't reach liquid nitrogen. And of course not 4 Kelvin. So therefore, you cannot have everything, so it just didn't work with our instrument. But it's a very good point, because you can learn really a lot from the spectroscopy. And there are many people that are doing excellent work. It was not enough.
Thanks. More question? Yes.
Thank you, Professor, for the presentation. I have a more fundamental question about the metallation reaction.
Yeah.
Is it easy to metallate a molecule on inverted structure or cell shape, or there's no influence of the conformation in the reaction of the metallation?
I have to think a little. Remember that. Actually, it turns out that that we did iron, cobalt. Iron is extremely reactive. It immediately reacts at room temperature. And we were at the beginning, we thought, because of this copper surface, you have this very strong interaction reflected by the. This would be the precursor for this metallation reaction. But it turns out that the activation barrier, so at room temperature, this doesn't melt. So obviously, this is a structure that it's energetically so stable that the metallation is not so attractive. And only go into higher temperatures than it goes. So the difference obviously is larger for the cobalt and on the copper. The state, the unreacted state goes down, so that the driving force gets less, and you, the decrease is lower. So it's yeah. Intuitively, we would have said, okay, this should be the fastest because it's sort of already a covalent bond. That's the difference.
Good, thank you. More questions? Maybe one last question. Maybe I'll ask final question. Inspired by what Abner said for photovoltaics with essentially chlorophyll. And you mentioned that you need a gradient to get the electrons out quickly, otherwise they will combine.
Yeah.
Can you tune the properties of your porphyrin film using stress, for instance?
Good question, I have no answer. What you can do is, that has been shown on magnesium oxide very nicely by the group of Martin Sterer and Graz. You can tune the interaction by changing the work function of the substrate. So like on certain oxide surfaces, there's a little oxygen deficiency or oxygen excess. You can change the works function quite significantly. And also if you have like a metal, then you have an oxide layer, and then on top of that you have the porphyrins, and then you really can also modify the chemistry. But this is exactly what we were talking about before. You change the energy levels, and that is possible, but extremely a future field. I think not everything is understood there. It's shown that it's possible, but showing it that it's working and then understanding it completely is then maybe a long way to go. I don't know.
Oh, thank you very much. So I think that's it. Got any questions? Let's thanks Hans-Peter again.
Thank you for this very nice discussion. I really enjoyed. I have 3 questions.
It was a pleasure.